Heat Exchanger Design Cooling System for MSU's High Performance Computing Center by Katy Sabo and Andrew Poteracki. Introduction and background. Shell and tube exchangers are one of the most common types of exchangers and are used in a wide range of pressures and temperatures. They consist of tubes mounted in a cylindrical shell. An example of what one would look like is shown in Figure 1. Because water flows out of a large reservoir near the engineering building and sent to various buildings on campus, the best way to reduce the high costs with standard refrigeration units is to reduce the cooling costs with drinking water by installing a shell and tube exchanger.
Analysis. The first law of thermodynamics was used to determine the amount of heat that could be produced with the cold stream properties. The heat that was allowed to be exchanged was 305 kilojoules per second. This Q was used to adjust the mass flow rate and the outlet temperature of the hot stream, and we chose to use water as the medium because it has a high thermal conductivity. The process data was set up as so, with the cold stream properties being determined with a mass flow rate of 43, the inlet temperature to be 57, outlet temperature to be 60 degrees, and we chose pressure values of a little higher than atmosphere on the incoming flow and then atmosphere pressure on the outcoming flow. And for the hot stream, the incoming temperature was the 90 degrees. We chose 86 degrees as the outcoming temperature and then used the Q to determine the mass flow rate for the hot stream. For our Aspen design, we chose to use an AEL configuration where A stands for channel and removable cover, E stands for one-pass shell, and L stands for removable channel with a flat cover. This allowed for the easiest design to be cleaned. The length and inner diameter were specified by the problem statement, and we chose a tube pattern of 90 degrees square for the most heat exchange, and we also chose aluminum 6061 because it was the cheapest and the lightest for our final design. The thermal properties for the water were defined at 57 degrees, 60 degrees, 90 degrees, and 86 degrees. Here we see our 90-degree square tube pattern inside the shell, and we also see the 20-foot length outer shell and the heat transfer graph that the Aspen gave us in the end. This shows the final design drawings that would be sent to a supplier so that our heat exchanger could actually be built. And here we can see a performance summary with a total heat exchanged of 336.7 kilowatts, which is pretty close to our initial guess, and also at the bottom a heat transfer resistance graph that shows the resistance from shell side to tube side.
In conclusion, the given parameters do not meet the 1 megawatt of thermal energy produced by the computers. The mass flow rate of the cold stream is fixed at 43.76 kilograms per second, and the flow rate needed to accommodate 1 megawatt of energy would require a mass flow rate from the cold stream of 143.12 kilograms per second. Since the mass flow rate required for the 1 megawatt is greater than the given mass flow rate, the conditions won't be met. The excess energy would require a standard refrigeration unit in addition to the shell and tube heat exchanger. The supplier chosen was Heat Exchanger USA. We picked this company as a supplier because of their availability of material needed for the design and their ability to design the shell and tube heat exchanger with the material that we requested for us.